Everybody, we are on SIG 13, which means if you're here, you're doing really well and you're getting close to being at the end, or you're just like, hey, I know how to do this one, or I kind of know how to do it, I still have to watch the video. First few questions on this are just testing your understanding of if you know what concavity is. So the definition of concave up is that if a function is concave up, then the slopes of that function are increasing. Right, what that means is maybe the slopes started as being negative, and then they get a little bit less negative, a little bit less negative, a little bit less negative, then 0, then a little bit positive, 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 right? So that would be concave up. But it doesn't always have to start negative, right? You could start at like 0 and then be getting steeper and steeper, or you could start with like a slightly slow one and then steeper and steeper, right? Those are all concave up. The definition of concave down is a function is concave down if, or when I should say, the slopes are decreasing, right? The opposite of concave up. So what that means is maybe you start with a positive slope, right? You start with a slope that's going up, and then it gets a little bit less positive, a little bit flatter, then it gets to 0, then it turns negative, more negative, negative, negative. So you imagine like maybe this slope was like 4, this one was 3, this one's like 1, the slope is 0, right? These are slopes. And then like this one was -1, -2, -3. You can see that the numbers, the slopes that go are decreasing. They're getting smaller, more negative. A point of inflection is the point when or where a function changes from concave up to concave down, or concave down to concave up. Right? That's part one of the questions. What is it? How do we find them? Well, they happen when the second derivative of our function equals 0, or when the second derivative of our function is undefined. Okay, so how do I know when let's pretend when I take my second derivative looks like, I don't know, like this. Let's say some blob, upper blob on top, and then there's another blob on bottom. If you want to know when it equals 0, then you set the blob on top equal to 0. If you want to know when it's undefined, then you set the blob on bottom equal to 0, right? So it'll be the second derivative will be undefined when the denominator is equal to 0 of the second derivative, and the second derivative will be 0 when the top is equal to 0, right? And so you'd set it equal to 0, maybe you get something like this, and you would solve this, right? You'd like oh, I'm add 9 to both sides, I'm going to take the square root, and I'm going to get plus or minus 3. Okay, so that's like what you're expected to say for this question is that right there. Okay, I was just trying to show you the rest there. All right, so here we go. Find the x-coordinates of all critical points. I guess I should have put a definition up there for critical points as well. And we want to find the open intervals where the function is increasing and the intervals where the function is decreasing. So the first thing we got to do is find critical points, right? Critical points are when the first derivative equals 0, or when the first derivative is undefined. So that same thing for concavity, except for the original function. So let's go ahead and take our first derivative, right? Our first derivative here is going to be, take the derivative, this is a quotient rule problem, right? So we're going to do u prime v minus v prime u over v squared. So u prime is 2x times v, which is 2x minus 4, minus v prime, which is 2, right? The derivative of 2x minus 4 is 2, times u, which is x squared, all over v squared. Right, so let's clean this up. My first derivative looks like this, 4x squared minus 8x minus 2x squared over 2x minus 4 quantity squared. All right, so we want to know critical values, which are when my derivative equals 0 or when my derivative is undefined. To find when y prime equals 0, we're going to take this top piece and we're going to set it equal to 0, right? So we're going to take 4x squared minus 8x minus 2x squared. Can we clean that up a little bit? 2x squared. This, if we combine like terms, we're going to get 2x squared here, right? I'm combining 4x squared with minus 2x squared. And we're setting this equal to 0, right? We're setting the top equal to 0. We can just factor this. We can factor out a 2x, and we'll be left with x minus 4. And so the critical values here are x equals 0 and x equals 4. This is when y prime equals 0. We also need to find out when is y prime undefined. To find when it's undefined, we set the denominator equal to 0, right? So we're going to solve this equation. We take the square root of both sides. Right, take rid of the squared. We're going to get 2x minus 4 equals the square root of 0, which is 0. And solve this, and we're going to add 4, divide by 2, we're going to get x equals 2. So there's 3 critical values. The critical values are x equals 0, x equals 2, x equals 4. So that's this question. We need to know when it's increasing or decreasing. So what do? We get a number line. We plot 0, 2, and 4. Okay, so what we need to do is we need to do some test values, right? I need to test a number in my derivative, because what we know is that if my y is like f is increasing when f prime is greater than 0, right? F is decreasing when f prime is less than 0, also known as negative. This is known as positive, right? So I need to check some numbers in my second derivative to see if the original is increasing or decreasing. So let's pick a number. How about -1, right? And let's plug in -1 to our original function here. Sorry, not original, into our derivative. Okay, so we're plugging in -1. We should be able to do this by hand. I do want to clean this up because I don't want to do the extra work. So I'm gonna erase this, right, and change this into a 2 because we're combining those two terms. Okay, and if we plug in -1 here, notice that the bottom, the denominator, is always positive, so we don't have to worry about that. -1 squared, right? I'm looking over here. -1 squared is 1 times 2 is 2 minus 8 times -1 is going to be plus 8, right? So we're doing 2 plus 8 is 10. I don't care about the number. All I care about is it's positive, right? Which means the function, the original function, was increasing. Okay, now let's take a number like 1. Let's plug in 1. We're going to get 2 here minus 8. That's negative. It's going down. Okay, let's try another number. Let's try like 3. If I plug in 3, we're going to get 3 squared is 9. 18 minus 24, that's also negative. Now we plug in 5. We're going to get 5 squared is 25 times 2 is 50 minus 40 is positive, right? So we're now ready to say, okay, the function is increasing on what intervals? Well, from -infinity to 0 and 4 to infinity. Again, you could use set notation as well. You could just say like this and like that. And the function is decreasing from, so we're looking now where it's negative, which happened from 0. So I'm going to be picky here. 0 to 2 and 2 to 4, right? Which I could also express as intervals. You choose one of those, right? So maybe you're asking the question, well, why didn't I include 2, right? Why are we not including this 2 here? Well, if you plug in 2 to your original function, right up here, you're actually getting a vertical asymptote, right? You're getting 0 on the bottom, right? So like maybe it's helpful to draw like there's an asymptote right here. It's an asymptote. The function doesn't actually exist there, so you there's no function value at 2, so you can't really include it in your intervals of increasing and decreasing. Okay, so we're done with that. The next one's asking find the x-coordinate is all points of inflection. Find the open intervals where the function is concave up and the interval is concave down. Again, so this is where we're talking about the thing up there. We're going to find the possible points of inflection, which involve the second derivative. So we're going to start with the first derivative. And then we're going to go to the second derivative. Right? And then based on what we said before, we find points of inflection by setting the first derivative equal to 0. When it's 0 or undefined, this one will never be undefined because the denominator is just 1. Right? There's no way to make 1 equal to 0. So we have this. We're going to go ahead and factor out a, well, I don't know, we could do this in several ways. Let's not factor, let's solve. Let's add 4 to both sides. We're going to get 4 equals 12x squared. Divide by 12, we're going to get 4 over 12 equals x squared. This is 1/3 equals x squared. You take the square root, and if you're not careful, you're going to miss one of the answers. This should be plus or minus the square root of 1/3. These are our possible points of inflection. To determine if they actually are points of inflection, we put them on a graph. So we're going to graph negative square root of 1/3, and we're going to graph positive square root of 1/3. And I only put 0 up there as a point of reference. We don't actually need to check 0. We just need to check a number left of negative root 1/3. Let's check, let's use negative 1 as our example, right? Where are we plugging this in? Well, we want to know when the second derivative is less than 0, right? We use the second derivative for concavity. So we're going to take this and we're going to plug it into our second derivative. Okay, if we plug in negative 1, it's negative 1 squared is 1 times 12 minus 4. We're getting a positive number here. So this is concave up. And then if I plug in a number in between these two, 0 is an easy one. You're just going to get 0 minus 4. This is negative. It's concave down. And then if I plug in a number right, I'm plugging in 1. And again, we're getting a positive number, which means it's concave up right there. Right? So we need to, you can't use this as an answer, right? You will get 0 points for doing that. It's just a tool to help us get where we want to get. We want to give the intervals. So we're going to say concave, let me not be lazy. Let's say concave up on the intervals. Let's do this notation first. Negative infinity to negative square root of 1/3. And square root of 1/3 to infinity. Again, these are not points, these are intervals, right? They mean the same thing as that. And then we're going to say concave down on the interval where this was negative, so from there to there, which was negative square root of 1/3 to square root of 1/3. Right, again, this is not a point. A lot of us still think this is a point. This is not a point. This is the interval x values between negative square root of 1/3 and square root of 1/3. Okay, let's just make sure we got all these correct. Okay, so they're going to use, they rationalized their thing here, but that's the same thing as negative square root of 1/3. If you don't believe me, plug them both into your calculator, you'll get the same answer. They didn't get that middle point of critical value, which I kind of disagree with. But they did get this, right? So that's why you should have checked that. The critical value should also have a 2 up here. So this one, you know, their answer key is not that great here because you see how they did get our same thing here. So we're good. We got everything correct. You know, good luck on this.